Welcome back from the break. As a Swiss person, I'm of course happy about the train system we have in Switzerland without all the delays and stuff. Sorry for now starting a few seconds later than in time, but I'm pretty sure SBB and Adrian will catch up.
Hi, I'm Adrian Burri. I'm working as a DevOps Engineer at the Swiss Federal Railways, SBB. And this talk will be a little different than the rest of the day, I suppose, because I realize there are a lot of platform people here with lots of open source contributor. And this talk will be about open source usage at SBB. And we rely heavily on what you platform people do for us, and we're really grateful for it. So I will show you what we do out of it and show you an application and the open source frameworks we're using in order to provide functionality to you. So let's dive in. I will start with a short overview of the state of open source, and then I will go a little bit into the field of train delay analysis so that you know what the application I'm talking about is actually doing. Before I will present you the main components of our software stack we're using for our big data application. And last but not least, if time permits, we will have a discussion and I will answer questions if you have any. So the state of open source at the Swiss Federal Railways is mainly a story about usage, a bit less about contributing. And even usage wasn't always the case that SBB was an open source company. You see, for instance, here until 2015, we had a lot of proprietary solutions, IBM, the ubiquitous Oracle database, and many of those closed source solutions. And starting from 2015, things started to change slowly, and the main driver behind it was a cloud-first strategy. And we had a platform, or still have a platform team, who heavily invested in bringing many of those open source components together and make an offering for the developers. So this is where open source really started to gain traction. And today, the standard stack for new applications at SBB is mainly based on open source. We still have a lot of these old applications that are slowly phased out, but right now we're moving in this direction. So, as I said, from the platform team, we have many of the DevOps tooling now is open source, but also the application framework, the standard Spring Boot with Angular, and Kafka replacing the old IBM integration bus technologies, and Postgres, the Oracle servers. So we're moving into the open source direction. In terms of contributing, there's also some news. Earlier this year, the Open Rail Association was started, and the aim is to foster collaboration of European rail companies. We have today a colleague from Deutsche Bahn who will have a talk, and he's also an active member of the Open Rail Association. So I won't go into details here. He is much more competent to tell you about it. But maybe I can give you some historical background why railway industry is maybe a bit late to the open source party here. You have to know, railway companies in Europe were and still are mostly state-owned companies. And as you can drive your car across a border, this is not something you can do with a locomotive. So you have very different regulations, very different technical solutions in every country. And countries like France or Italy even have different voltages. So you cannot easily take a piece of equipment and go to the next country with it. And this was a political decision mainly. All the countries wanted to protect their railway industries, and it was only, I would say, after 2000 that the European Union Agency for Railways started an effort to harmonize the regulation. So there are more open standards, more technologies, open technologies coming to the railway sector, and this is gaining traction slowly because we heard in the last talk the life cycle in a cloud environment can be several days. In railway industry, we still have relay interlocking systems dating back 60 years, so that the life cycle is rather in decades. So it takes some time until new technologies really start to gain traction, and so I expect to be a slow adoption there. As I talked about the Open Railway Association, this is another example I want to show where this open source movement is starting to take on. And this is the development of a new driver advisory system. This is a national initiative, so it's being developed by SBB IT, but it is also for other railway companies in Switzerland like BLS and SOB. And this per se is not something new. The SBB as an industry leader in Switzerland has been developing software for other railway companies all along, but the first time now it's based on an open source license and it's built on open standards. So the other railway companies now have the possibility to use the software as they want to make enhancement or even go into collaborations with industrial partners to realize their own opportunities. So to summarize, at SBB we're rather a company of open source use and not so much of contributors, but I expect to see this changing also in international collaborations. So this was about the open source part. Now let's dive into the business context. And I'm aware you're all technical people, so I want to keep that short and not to bore you with the details. But there are a few things you need to understand about the application. So Roger already started with that, and I use this, of course, again. Punctuality, the current punctuality number, that is the passenger train punctuality for last year in Switzerland, was 92.5%. That means 92.5% of the passenger train arrived at the passenger stop with less than 3 minutes of delay. Now, for those of you who are not familiar with punctuality numbers, this is really this is really the best in Europe, and it's on the same level as the world leader in Japan. And I know the German colleagues will look at this number with envy. Sorry. So then the question is, what has it all to do with what I'm talking about today? And the application we're developing is really looking at this remaining 7.5% of passenger trains. So we analyzed the delays, try to figure out dependencies and the root causes so that we can improve further. Because train punctuality, of course, isn't something that happens per se. We have a lot of focus there and try to improve always further. So now here's about the application train delay analysis. There are 3 main pillars of data producers we're using. The first one is planning. Of course, we have the timetables we're using as a baseline, but we also have all the information about connections, rolling stock planning, construction sites, stuff like this. This gives us the baseline, what we expect from our railway operations. Then we have the data from the operations per se, that is the actual time. The rail control system gives us, for every train running on the Swiss network, at any relevant position, the passing time. So together with the timetables, we can figure out where we incur a delay. And even more so, because we also know the network topology, we can decide where one train blocks another or has to wait for a connection. And this input we're using to build a graph like this. So every dot here is a deviation of a train at a particular point on the network, and the arrows depict which other trains they influenced. So with all this data, we can have this delay graph, but what is still missing is the information, what actually is the root cause of a delay. And this is where we use the third input, the dispatching data. Swiss railways are controlled from 5 control centers in Switzerland called Betriebszentrale. And there the dispatchers oversee the network, and they take notes of all the incidents they're seeing. And they do this by entering in a kind of a ticketing system where they enter the root cause and also the actions they're taking. And we're using this input mainly to identify the root causes. Now, root causes, that can be anything, and you probably know it, a defect door, or some other defect, be on a vehicle or wayside device, or even more exotic cases like missing train personnel. Trains don't run without driver. And this happens. And I want to show you one very special example. I actually took it from an English newspaper about the Japanese railways, but the very same event happened for SBB last year. And it was a snail that sneaked into a wayside device, causing a short circuit and causing the device to fail. And this is an example of Code 91 special environmental conditions. Things happen. Okay, but as you see, it's not that easy to have a railway system where you're punctual all the time. There are so many reasons from punctuality, but you can work on it and try to improve. And this is what our application is about. Oops, it was the right direction. Okay, so. This was the part about the business context, and now I will go more into the technical components of our solution. As I said, this is a big data application we developed, and we built it exclusively from open source components. Whoops, wrong direction, this one. Okay. Here's an overview of the components we're using, and I will talk more about the main components later on. So it's Apache Spark as an analytics engine. We're running on a Kubernetes environment and using Iceberg tables. But I want to point out also the components on the right-hand side. And here we have mainly applications for operations and monitoring. And as I said, we have a platform team who really make this offering. They make an integrated environment where we can all have all these components really with a self-service portal. And I think this is really crucial, because the application we're developing here, we're only 3 developers. And we wouldn't be able to handle this complexity here. So we're really glad that you operations people provide us with the necessary tools. And this really helps us to bring customer value to our customer. Okay, so let's dive in. The first component we're using is Apache Spark, and I suppose most of you know this. It's a unified engine for data analytics, and it was developed at the University of Berkeley in 2009 already. So this is really, not in terms of railways, but in terms of IT, it's a really old open source project. And it still has a very vibrant community, and this makes it for us a really good choice to build our software on it. And to understand why this is such an important tool, you have to go back in the time when it was invented, because then the predominant framework was MapReduce, and this was very complex to develop. You had parallel programming, and it was very slow too, because you had to write every intermediate result back to disk. And what Spark offered was the concept of a resilient distributed data set. That means that your whole data, from a programmer point of view, you had a serial programming model, and Spark takes the pains to distribute the code accordingly and to work on a distributed data set, even hiding the aspect of resiliency too. So this is really important, but of course Spark hasn't stand still in the last 15 years, and there are many other features that have been developed in the space that make it a good choice for an open source stack in big data analysis. One is the serial programming model we had already, and the other is in-memory processing. So you don't have to write everything back to disk, but you can process it in memory. And of course, you have a great versatility. Today, you have so many connectors. You can use every data source as sink or as source. File-based, DBs, messaging, you really can connect to any technology mainly. And also you have many use cases built on top of Spark. You have, for instance, Spark SQL, which makes Spark into a framework for data science analysis. You can do Spark streaming. You have libraries for machine learning and stuff like this. So this makes it a really good choice to start with big data analysis, because it offers you possibilities, and very many possibilities, many use cases. So Spark, when we started using it, we used Spark on a Hadoop cluster, and this was some kind of a drawback, because Hadoop cluster, although based mainly on open source components, is very hard to operate. And we also had an external distribution and an external provider which operated it on premises for us. And when it was announced that also the big data part of the SBB application stack would be cloud-based, we took the opportunity and take our Spark code and try to running on Kubernetes. Now, Kubernetes is definitely not the technology I have to tell you something about. They know much more about than I do. But there's one special aspect maybe, and this is to understand why Kubernetes is well suited for big data applications. Because the Hadoop platform had a quite unique architecture in the sense that you had data nodes, and that you would push all the application code to the nodes and try to have data locality as much as possible. Kubernetes takes the other way around. You have compute node, you load the data, you process, you store back down. And if you're like me, a guy who grew up in the 90s with dial-up modems, then you know networks can be very slow and very painful. And also very unreliable. So when I first started with proof of concept, I thought, well, this is all nice, but it's never going to be as performant as on the Hadoop platform. And I realized the performance in the Kubernetes cluster is actually the same. And I think the platform people will be able to explain to me why this is the case. I was really astonished that this is the case, and it's a testament to how fast and of the bandwidth of the today cloud providers network are. I didn't really expect that. So, being in a cloud, in an open source, on a Kubernetes cluster, brings us another advantage of cloud. Namely, we have almost infinite cloud storage available at almost no cost. And this brings us to the last component we're using. This is Apache Iceberg, which is an open table format for analytics. Why are we using this? Well, the blob storage in a cloud environment is all nice and good, but in terms of applications we are developing here, we need something more structured, something more table-like, schemas and so on. And this is what those table formats like Apache Iceberg, Hudi or Delta Lake are bringing to the table. So what they're actually doing, they store the data still as data files in the blob storage, but they have a layer of metadata which describes the schema, the structure of the data tables, and you're also able to have different snapshots of the data in parallel. This is not a new concept. This was already introduced with Hive tables on the Hadoop platform 10 years ago, but these new contenders in the field are pushing this idea further. So today you can have correctness through ACID transactions as in a regular database. So there's maybe one difference I have to point out here. Regular databases would have a database engine as a service somehow and hide away from you the data layer. And these open table formats, they're actually doing the opposite. So there's a spec how this data is organized, and you have a driver which lets you access it from an engine like Spark, for instance. And this lets you scale more easily than with a database engine. So we are stuck with the correctness and transactions. What it also gives you is efficient query planning. When you have just a data lake with no structure, then you have to read all the files to figure out where your data is. And here with the metadata, you have also statistics about all the data files, so it allows you to have efficient query planning and with this efficient query execution for your application. And you have other advantages like schema evolutions. When you have terabytes of data, then you don't want to rewrite all your data just because you add a column to a table, for instance. And this is what those technologies offer you. So I realized I was always, as always, very much faster in the real talk than when I practice at home. So we are almost through, and I just want to reiterate the key takeaways. So analytics workloads today are possible on a software stack purely built from open source components. And what is really helping here is a cloud environment where we can have analytics engine like Spark running on the same runtime we also use for transactional workloads, and we can have this open table formats for an efficient cloud storage. So I'll leave you with this. I hope you have some questions left.
Thanks for the talk. You mentioned at the beginning that's a transition from as proprietary software to open source components. And obviously, it's not as easy as shutting one server down and turning another one on. So how can I imagine is the migration of all the data handled you are then running your analysis on, or is there even any value in such old data?
Yes, actually we are moving all the old data from the Hadoop platform over to the cloud, and yes, there's definitely value in this. This takes a bit of effort, but this is slow compared to the effort of rewriting the analytics application here. So, but we have data back to 2010, for instance, about the infrastructure network, and yeah, we still keep this data.
So I've seen this talk in Leipzig at the Chaos Computer Congress about mining data of the German railways, where they figured out that actually the delay number they specify actually doesn't include the cancelled trains.
It's not quite the case here. Switzerland does account for cancelled trains.
Perfect.
Partly. It's not quite the same. And we also have another punctuality definition. I think in Deutsche Bahn it's 6 minutes late is considered a late arrival. With Swiss trains it's 3 minutes of arrival, and it's considered. So these delay measures are not unified across the different railways, and the numbers are not always that comparable.
Customers would be happy if it's at least 15 minutes.
Question? You mentioned that you're a very small team. So why did you still go for an open source solution if you could have picked the cloud providers offering? Because those are mainly based on open source solutions as well, right?
So, as I said, we're a very small team developing the application, but we can rely on the platform team. So the Kubernetes cluster we already had, so we didn't have to use something there. And we already developed the Spark application on a Hadoop cluster before. So it was mainly a question of lift and shift. And we looked at those offerings, like, for instance, Databricks. And they're often, either they're based on a Hadoop platform, which we didn't want anymore, or it was like Databricks, clearly focused on one single use case. Databricks is very much focused on data science, and that's not what we're doing. This is really, as I said before the talk, it's a bit a normal application disguised as a big data application. So we're quite low on data and quite heavy on logic. So this setup made much more sense for us.
Question here?
Yeah, the comment about the different statistics on how to measure punctuality is quite interesting because, I'm working from Deutsche Bahn, so thank you for the comments here. Anyway, different discussion. So we also have, as far as I know, I'm not an expert there, different ways how to measure punctuality, and by the way, also other published statistics that are not only based on these 6 minutes, but actually on the lost units, like when also broken connections appear, then this punctuality or the loss of punctuality is even worse. So do you also have like internal other statistics how to measure punctuality, or is everything just these less than 3 minutes? No matter
Yes,
if I miss my connection in the next train station, for instance.
We have a large bunch of punctuality numbers. And I even got a presentation from the punctuality guys in preparation for this talk, and I decided to leave it out because it starts getting confusing. And this is exactly the case. Now, you can tweak your punctuality by breaking connections. Great, you can leave your passenger behind and start a journey without delay if you don't take the connection. And this is what I mean. You shouldn't take the numbers as this, you have to compare how they're measured and what they really mean. So we have, for instance, passenger delay as well. This is a train punctuality number I showed you. Lots of differences.
Thank you, great talk. I have a question related to, I saw both Spark and Kafka, and the platforms have both like streaming capabilities. And I'm just wondering if you have like some streaming pipelines going on to actually see those statistics kind of daily life, or it's like more, you know, analytics going afterwards with more precise numbers.
This application here really is batch processing. So we're processing the data after the fact. What I forgot to talk, there are two main purposes. One is for analysts, that they can see the actual mechanics of a delay, and the other is to have statistics about which causes improve, which causes get worse. And there, all you need is batch processing. There's no benefit in streaming processing. But we actually do streaming analytics where we process all this connection information, timetable information in real time for analytics solution to figure out what is going on the network.
One more question here.
Yeah, one more. You said that part of the attraction of the open platforms is that you can share also in the context of the open railways. Is this going to be a new business model for the SBB, that you start to sell that on a grander scale?
I don't think so. There has been some efforts in the past, and we realized it's not our business model. And you also have the problem that many of these developments are funded by the authorities, and they want some specific outcome for it. They don't pay for a product you're selling afterwards. So there is also this barrier a bit. It's public money. We cannot do everything we want with it. So no, selling is not something we intend. I hope we see more sharing of code between railway companies, because I think this is where we have the way forward, and to actually optimize costs for all of participants. As we said before the talk, we're not in competition with Deutsche Bahn. We're really partners, and when we can profit from one another, it's a gain for both.
Super interesting talk. I was wondering what were some of the most interesting things you figured out when doing this analysis for train delays. Something interesting you found out there?
Well, I do mostly the programming. You should ask our analysts. There are some things which I find interesting. There are events. Usually the graphs look as I showed. It's some 4 or 5 trains, and then actually the delays get aufgeholt, so the trains catch up. But when really something heavy happens, then you see a graph that really fills the screen, and it's like a complete breakdown. And there are several incidents, and an interesting part of research would be what would trigger that an event becomes really a system-wide event. And I think we have the data to investigate that, but sorry, I can't tell you the result now. I don't know it yet. But who would have the data?
Hi, thank you for the talk. On one of the first slides, you showed the technologies, and I know that you use more technologies than I saw on the slides. What does it take to get on this slide?
Mostly my short-term memory. The technologies that are on the slide are the ones that I most work with. Which one did you miss?
Flutter?
No, we don't use it all. at least not in our project. If you talk about the technologies on SBB, then I think the slide is much too small. Then we have all kind of stuff. These are really the most important frameworks, and yes, of course, there's lots left out.
Okay, so this was only for your project.
No, the initial slide was more about the main technologies we use. But as you're completely right, we use Flutter. We have a lot more DBs. Like I know a project using Cassandra, for instance. In SBB IT, we're quite free to choose the technology that suits. We have a platform team that offers a lot, and we can use it to our benefits. But if we think that there's something better and we're willing to operate it ourselves, then we can use it mostly.